Thank you for the invitation, Daniel and David. I'm happy to present our new EIP's work, Flow Factorized Representation Learning, which is a joint work by University of Trento in Italy and University of Amsterdam in the Netherlands. So in this paper, we want to propose some novel definitions of generalized equivariance and disentanglements. So we propose our Flow Factorized VAE variational autoencoder. And this is the high-level overview of our framework. We have the pixel space and the latent space. Between the two spaces, we have the encoder and decoder mapping to make them connected. In the pixel space, we have different transformations we would like to model. And in the latent space, we have their corresponding vector fields, which is the velocity applied on the latent samples. The time evolution of each latent samples follows the continuity equation, or the focal Planck equation, and the evolution of each latent samples is enforced with the Hamilton-Yardwick equations to ensure that the motion is optimal transport. So we see our framework can allow for some new understandings of generalized equivariance and disentanglements. And here, the equivariance means that any transformation in the pixel space can be modeled by the process of encoding and latent flow, and then finally decoding. So our latent flow is actually the equivariance operator defined in the latent space. And the concept of disentanglement means that the traversal directions at each latent samples are actually the distinct tangent bundles following optimal transport. And disentangled representation learning. And we are somehow trying to unify these two concepts. So here is the traversal results on different data sets. So we see our framework is more, can have very precise control on the transformations. And this is the graphic model of our framework. So we have the observed variable x, the transformation variable k, and the latent variable z. So here we factorize the joint distribution of the latent variable z into a Markov chain, which means that the current states only depends on the previous one. And the transformation variable k is used to guide the latent flow process. The case to tell the latent variable which transformation is being applied in the empty space, and which path we should follow. Here we also have the weakly supervised sighting, which means that the transformation variable k is not observed, but it's inferred from the sequence of x, and then we use the inferred k to guide the latent flow process. And since for both the prior and the posterior, since the induced velocity fields can change the probability density, so we have also the normalizing flow like conditional update of the prior and the posterior density at the different time steps. So here f is the function of the latent, f and g are the functions of the latent sample change. We just enforce the a scalar potential field and use its gradients as the vector fields. So for the prior distribution, since we have no prior knowledge of the sequence, we don't know what transformation is applied in the image space. So we just use the diffusion equation to model the prior evolution as a random diffusion process. And for the posterior, we take the potential as a function of the z and t, and we use the gradients to derive the conditional update according to the normalizing flow like update. And here we also derive the evidence lower bound of our framework. So when k is observed, our framework is supervised, and we have the we have the evidence lower bound, which is like the reconstruction term, and the curl diverges between the posterior and the prior. So when K is not observed and is inferred, so we use another posterior to infer K from the sequence X bar. And here in the evidence lower bound, we have a new term, which is calculated as the curl diverges between the posterior of K and the category distribution of its prior. Okay, so here we have some qualitative, So here we have some quantitative evaluation. So in this table is present the equivalence error and the log likelihoods on different data sets. So here the equivalence, for the equivalence error, if the value is smaller, that means that the model has better performance, because this means that our model is more approximately equivalent. So we see our method has better equivalence error than the baselines, and it also has better log likelihoods. And this is the qualitative evaluation. So the figure on the top left displays the different transformations we model on the data sets of Factorized 3D and Isaac 3D. We see our method can control the image transformation very precisely, and it's more disentangled than the baselines. And the figure on the top right shows that our method is more flexible than the baselines, which means that during the traversal process, we can switch the latent flow operator. For example, here we can switch the transformation from the rotation to the curving, and here we can change from the wall hue to the object hue. And the figure in the bottom left displays that our method can be flexibly combined. So we can combine our latent operator. So here we combine the wall hue and scale, floor hue and object hue, and the scale and the object hue. This shows that our method is very flexible, and it's linear composable. So it means that we can combine the transformations linearly as we want. And the last figure shows that our method is robust to all of distribution samples. So here the model is trained on the MNIST data size, but the test sample is taken from displays. So we see our VAE has better reconstruction results, but the equivalent operator still manifests in the latent space. Okay, that's all.